So first, let's talk about limits as x approaches infinity. And what I would kind of like to point out is, to me, there's a few different varieties of these. So there's kind of the lovely run-of-the-mill nice ones, which are, in my opinion, ones that look like this. The limit as x goes to infinity of some nice like 5x squared plus 7 over 2x squared minus 3x plus 1. In my opinion, that's a nice one because all you have to do is divide everything by x squared, or whatever the highest power of x is in the denominator. So if we do something like this, we divide by x squared and we get the limit as x goes to infinity of 5 plus 7 over x squared over 2 minus 3 over x plus 1 over x squared. And then we use the idea that all these things that are being divided by something that's like x to a power, all these things are going to get smaller and smaller and smaller as the x values in the denominator get larger and larger and larger. So this limit ends up being 5 halves. You have a question, comment? Oh, that's how you raise your hand. And they're fairly quote unquote nice, as long as the power on top is smaller than or equal to the power on the bottom. I should use the word. As long as the degree on top is smaller than or equal to the degree on the bottom, the highest power. So this would also work out just great if there was a limit as x goes to infinity or minus infinity of 2x cubed plus 4x minus 1 over x to the 6th plus 7x to the 4th plus 3x minus 2. This one, you would do the same sort of thing. You would divide everything by x to the 6th, and you would end up getting 0, which you could certainly justify to yourself in a kind of very I'm going to show the work, but the hand-wavy kind of justification here is that, well, of course it's going to be 0. Of course it's going to be 0. It's going to be 0 because the denominator is a much, much larger thing than the numerator. X to the 6th gets bigger way, way faster than 2x cubed. So that's kind of the not very proofy way of doing it, not very not sure how it works. But the actual way we do this is the same process. You're going to divide everything by the highest power of x in the denominator. So I'm going to write this as the limit as x goes to infinity of 2x cubed divided by x to the 6th plus 4x. I didn't actually mean to show all this work, but whatever, it's fine. Everything divided by x to the 6th. Okay. And then simplifying all those terms, we have the limit as x goes to infinity of 2 over x cubed plus 4 over x to the 5th minus 1 over x to the 6th, all divided by 1 plus 7 over x squared plus 3 over x to the 5th minus 2 over x to the 6th. And what we're going to see again, just like last time, is everything that's being divided by x to some power is eventually going to get very, very small because you're just dividing by a bigger and bigger number. So all these things that are like 7 over x squared or 3 over x to the 5th or 2 over x to the 6th, all those go to 0, and we're left with a 0 plus 0 minus 0 over 1 plus 0 plus 0 minus 0. And 0 divided by not 0 is just 0. The slightly less nice, but still in the same category of types of limits like this, of a limit of a rational function, is when the degree on top is larger. When the degree on top is larger, it is a little bit dicier. You have to be a little bit more careful with that because your answer is typically going to be some sort of infinity. For the same sort of reason that this one was 0, right? In this one, the bottom was getting much bigger than the top, so the overall fraction was big thing on bottom, less big thing on top, so the overall value was getting smaller and smaller. If we flip that over, now the top is bigger and the bottom is smaller, you're going to end up getting something where you have something that's getting larger and larger and larger. But it might be negatively large or it might be positively large, depending on how things are working. So let's look at something like the limit as x goes to infinity of, I want to make it so it turns out to be negative infinity. Let's say we've got something like, negative 2x to the 5th plus 5x cubed plus, that's fine choice. Yeah, sure, Dane, sure, that's fine. 7 over, yeah, 4x squared plus x plus 1. I probably left myself some room. So just like the previous two examples, I'm going to divide by the highest power of x that's in the denominator. Always in the denominator. If you divide everything by x to the fifth here, it becomes really, really unclear if our answer is positive or negative. So I'm going to divide everything by x squared. So I'm going to write this as the limit x goes to infinity. I'm going to just do the work and not actually write all this stuff. So dividing by x squared, I get negative 2x cubed plus 5x plus 7 over x squared over 4 plus 1 over x plus 1 over x squared. And now here's where you have to be a little extra careful. I'm actually going to do one more step before I do this. So if I were to plug in infinity right now, look what happens. I get minus infinity plus 0 over 4 plus 0 plus 0. But the minus infinity plus infinity is, it's actually indeterminate. Minus or infinity minus infinity, right? We don't know. Now, you could argue here that that infinity is much bigger than that infinity. So this negative infinity is going to overpower this positive infinity. And it's totally true. But the more precise way of doing this is to rewrite it in the following way. I'm going to write this as the limit as x goes to infinity of, and I'm going to factor out an x from just these first two terms. Check this out. I'm going to have x times negative 2x squared plus 5 plus 7 over x squared and all the rest on the bottom. So now I'm going to actually do the plugging in of the infinity. Hopefully I have enough room. I think I can make this fit. So x is going to infinity, so I have infinity times infinity squared is still infinity, times negative 2 is negative infinity, plus 5 is still negative infinity. And then 7 over infinity is 0 over 4 plus 0 plus 0. So I have infinity times negative infinity, which is negative infinity, divided by positive 4, which is still negative infinity. Basically, you're just trying to figure out what the sign of this infinity is. So this rational expression, to the right anyway, is going towards negative infinity. To the left would be going to negative, negative, positive. The left would be going to positive infinity. So if you were to find the limit as x goes to negative infinity of this, you would end up getting a positive infinity as a result. Kind of
so the only form of infinity that is indeterminate is infinity minus infinity and infinity divided by infinity?
No.
What else is indeterminate?
Infinity to the 0th power.
Does that come 1?
Yes. Also 1 to the infinity. We've already talked about it. So you might have, so just as a quick aside here. Oh, sorry. That's why it's on the side. So the limit as n goes to infinity of 1 plus 1 over n to the n. Do we know what that limit is? Right, what is that limit? Just e. But look, that is literally a 1 to the infinity type. The inside part here is getting closer and closer and closer to 1 plus 0, and the exponent there is getting larger and larger and larger. So this is what's called a 1 to the infinity type of indeterminate form. Now I want to stress, it is not actually 1 to the infinity of power, right? You don't have 1 times 1 times 1 times 1 times 1 times 1 forever, because that would just be 1. You have a number that is very, 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 very close to 1, but still not 1. In this case, a little bigger than 1, although it could be a little smaller as well, that would work out too, raised to an ever-increasing power. And so like if you did like 1 plus 1 million to the millionth power, it's going to be very, very close to 2.7. Because even though you're very close to 1, the number of times you multiply with that 1.0000001 by itself overcomes how small it is or how close it is to 1 to get you back to something else. And E is the number that this thing gets closer and closer and closer to as n gets larger. We'll talk more about these indeterminate limit forms, specifically the exponential ones, after we have learned L'Hopital's rule. Because to actually prove this limit, to actually find this limit requires using L'Hopital's rule, or at least the way I'm used to doing it. So definitely for sure later on, like in chapter I think it's the end of chapter 3. We'll talk about L'Hopital's rule, and we'll talk about how to do limits like this, which is kind of cool.
So I don't think that someone is a little bit tricky with extrapolating infinity and
Mhm.
rational function, and furthermore, the top has it as square root.
Right, that's exactly where we're about to get. So let's look first at this. So sometimes they just start off actually that way. So I'm going to do that first, and then we'll come back to that question. Is just kind of a modified version. So let's say we want to do. I gotta make sure I think of something that's not going to turn out stupid. Let's say we want to find the limit x goes to infinity. I'm just going to make it nice and easy, not crazy. Let's say we want to do something like, yeah, 4x plus 7 over the square root of 9x squared plus 2. I want to find that one. And I also want to find this limit. The limit as x goes to minus infinity of the same thing. So what I would tell all of you is that this sort of so these are the less nice ones, where you have something like infinity over infinity, but now it's not exactly a rational expression. Right? It's right, because it's not a polynomial on the bottom of the square root. But it's kind of like a rational expression. Right? You essentially have a degree 1 on top, you kind of have a degree 1 on the bottom, because the square root of x squared is kind of like just x. So to make that more accessible, what we're going to do is we're going to, there's a number of ways of approaching this. My typical way of doing this is to pull out an x from inside the square root. Meaning I'm going to rewrite this as the limit as x goes to infinity of 4x plus 7 over the square root of x squared times 9 plus 2 over x squared. And then we pull out the x squared from the square root. The square root of x squared is, yeah. So you get the absolute value of x times the square root of 9 plus 2 over x squared. And now, since x is positive, how do I know x is positive? Because we're going to infinity. That's about as positive as you can be. Since x is positive, we can say that the absolute value of x is just x. So 4x plus 7 over x times the square root of 9 plus 2 over x squared. And then, just like in the problems before, I'm going to divide each thing by x. So I'm going to write this as a limit as x goes to infinity of 4x divided by x, 7 divided by x, over x times the square root of 9 plus 2 over x squared divided by x. Each thing that's added or subtracted together gets divided by x. I don't divide each of these parts by x, right? Because then I'd be dividing that term by really x squared. Right, so if things are multiplied together, each factor doesn't get divided by x, just the whole thing. Thought there was, I think I recognize that student, but not quite sure who that was. That's all right. So x is canceled here, x is canceled here, and we're left with the limit as x goes to infinity of 4 plus 7 over x over the square root of 9 plus 2 over x squared. And then all the things being divided by x, or x to some positive power, are going to go to 0. So we're left with 4 over the square root of 9, which is 4/3. On the other side of things, if we go towards negative infinity instead of towards positive infinity, the answer is going to be a slightly different question.
I don't think we have like square roots on the bottom.
You can totally have square roots on the bottom. So the thing is, you might have been told at some point that if we were to simplify this expression, we should simplify it by rationalizing the denominator. Sure. Which is so totally, like if someone were to say something like simplify this expression, and I had, like something like 4 over the square root of 5, the way I would simplify this would be by multiplying by radical 5 over radical 5 to get 4 root 5 divided by 5, because it's considered simplified to have a rationalized denominator, aka a denominator that does not have any irrationals or radicals in it. But if we're just trying to deal with a limit, we don't typically have to adhere to that particular thing. Welcome. So yeah, we're totally allowed to deal with the square root in the denominator. Now, I will point out, if this hadn't been a nice number to take the square root of at the very end here, like if it had been 4 over the square root of 5, I might have rationalized. I probably wouldn't have, to be honest. Like, so totally we rationalize things if we're asked to. But typically it's not something I want you to focus on. Simplifying, although important to be able to do correctly, is kind of low on the list of things that are important to us in this class. We want to be more focused on being able to correctly evaluate limits and then maybe simplifying the answer at the end, or to find derivatives and then maybe simplifying the expression at the end. It does become more important when you start trying to maybe find where you have a horizontal tangent line or a critical point, because then you're taking your derivative and setting it equal to 0. And to solve that equation, it is typically necessary to simplify the derivative to be able to solve that efficiently. So it is important to be able to simplify. It's just not as high on our list of things that are important. Okay, so looking at this other limit here, we're going to see that we're going to get something slightly different. Welcome, come on in. Talking about some limits to infinity. So if I start simplifying this, the same first steps are going to be the same until I get to here. So this is totally equal to the limit as x goes to minus infinity of 4x plus 7 over the over the absolute value of x times the square root of 9 plus 2 over x squared. From here to here, all the steps are the same, except it's going to negative infinity to positive infinity. But now at this next step, we have to make an observation that's slightly different from before. Here, the absolute value of x was just good old x, because if x is positive, the absolute value of a positive number is positive number. But here, since x is very, very, very negative, the absolute value of x is no longer just x. The absolute value of x is going to be negative x. And then everything else is still the same. I see nodding heads. I feel like everyone's cool with that. I know I've said it a lot of times, right? But like, we're hopefully, I can say it again. Like, I think everyone, I'm gonna say it one more time, just so everyone's cool. Just to make sure everyone's cool with this, right? The absolute value of 5 is just 5. The absolute value of negative 5 is, you write it is just 5, but the way we get there is by saying it's negative 5. So that's how you take a negative input and turn it into the positive thing. That's how we're taking our negative input and turning it into the corresponding positive thing. Cool. So then the work is the same. The only thing that's going to be different is we're going to end up with a negative value instead of a positive value this time. So we're going to end up getting, divide everything by x. So we're going to have the limit as x goes to minus infinity of 4 plus 7 over x over negative 1 times the square root of 9 plus 2 over x squared. And then letting all the x's go to infinity, all those things go to 0, and you get 4 over the negative square root of 9, which is negative 4/3. So this function and functions like this are examples of functions that have two different horizontal asymptotes. Positive 4/3 to the right and negative 4/3 to the left. Kind of interesting. Yeah. I wouldn't say always 100% of the time, but it's a good bet that that is likely to happen. I try to refrain from saying anything's going to happen all the time because often there are kind of sub cases and stuff. Yeah.
Can you talk about an example where there are two x's and within the square root of different powers?
Sure. Yeah. Sure. So actually, I wanted to go back to the example that you had asked me. What was the one that you had showed me before? It was a square root minus another square root.
Yeah.
Cool. Yeah. So let's say we have something like, I'm going to change up a little bit just to make it more fun. Let's say it's something like the square root of 25x squared plus, I'm going to make the numbers terrible, 19x minus 5x. Yeah. And so this is another indeterminate form. So I just want to point out, indeterminate forms are just fancy words for do more work. That's all that really says. You got to do more work. We have a few of them so far. We have 0 over 0. That's kind of our favorite indeterminate form. Got to factor, cancel, do whatever, algebra. We also have seen some infinity over infinities. And there's also infinity minus infinity. There's a few other ones that we haven't quite gotten to yet, like 0 times infinity, infinity to the 0, 1 to the infinity, and 0 to the 0. Those are also indeterminate forms. Again, they don't literally mean those things. They just mean like here, right? I'm not literally doing infinity minus infinity. I'm saying this is something that's getting very, very big minus something else that's getting very, very big. Just like a 1 to the infinity is something that's getting very, very close to 1 raised to a power that's getting very, very large. Okay. We're going to use our typical kind of algebraic methods here. We can multiply by a conjugate. So we're going to rewrite this as the limit x goes to infinity of the square root of 25x squared plus 19x minus 5x over 1 times the conjugate. Square root of the same thing plus 5x over the same exact expression. Okay, so then we multiply out the conjugates and we don't multiply out the not conjugates. Meaning I'm going to multiply at the top. I'm going to get, be careful here, 25x squared plus 19x minus 25x squared. The middle terms go away, right? That's why we multiply by the conjugate, because we don't get middle terms. Or I should say, they cancel each other out. And then on the bottom, so on the bottom, I'm going to start working towards where I need to work towards, which is I know that inside the square root, I want to factor out the x squared. That is typically our plan of attack for dealing with a square root of some stuff. So I have a square root of factoring out the highest power of x is what I should really say, although it's typically an x squared. It should really be an even power. So it should be like an x squared or an x to the fourth or an x to the sixth, something that you can nicely simplify. And then I have left over a 25 plus 19 over x. And then still my 5x over here. All right. And then on top, the 25x squared and the minus 25x squared subtract to 0. So we're left with a limit as x goes to infinity of 19x on top over square root of x squared is the absolute value of x. And then you have the square root of 25 plus 19 over x plus 5x. And now here's the point where if we were going to negative infinity, we would have to say that this was the absolute value of x was equal to negative x. But we're not going to positive infinity, so we just drop it. We say, okay, great, that's the limit as x goes to infinity of, I'm gonna leave myself some room here. So I'm gonna write this as x square root of 25 plus 19 over x plus 5x. And I'm gonna also do the work of dividing each thing by the highest power of x that's in the denominator, which is just x to the 1. So then we simplify. We get the limit as x goes to infinity of 19 over the square root of 25 plus 19 over x plus 5. Now we finally are able to take the limit. There's no longer infinity over infinity type. So this goes to 0, and you're left with 19 over 5 plus 5. 19 over 5. I will point out that this sort of limit, like if you rewrite it like this, is another example of a limit that where eventually once you learn it, you could, you shouldn't apply L'Hopital's rule. This is totally infinity over infinity, and you can use a L'Hopital's rule for infinity over infinity, but it doesn't end up working out here. You get in this infinite loop of just doing the same thing over and over again. So sometimes L'Hopital's rule, even though it's technically applicable, and I know we haven't talked about it, like I know I keep saying this thing, you maybe never heard of it before, but just be aware that it's a rule we're going to learn later. We're taking limits, and sometimes it's a really great tool, and sometimes it's a really crap tool. Okay, yeah.
So look at the strategy that you're using to get the x out. That's a strategy I've never seen before, but it seems to work. So
You mean from here to here?
Yeah, you factor it out, take it out. Is that a strategy that sufficient for most of the problems that we're going to encounter? Or do we need to, because the way that I've been told to do it is to divide everything by x, but the inside you divide it to the power of x that has the
Right. The problem with that is if you're going to negative infinity,
yeah, it becomes problematic.
it becomes, you have to be just a little more careful. So I mean, it's it's really the same work, it's just kind of attacking it from a slightly different side.
So which one do you think?
I would do it this way. I typically, unless I have specifically said so, I'm going to show you the way to do it that I think you should do it. Not that there aren't other ways of doing things all the time, but I will usually try to show you the way that I think is the easiest to understand and the easiest to do.
He
So,
did the same thing, but he did it in a much more complicated
of
way.
course,
He didn't explain his steps, but now that I'm looking back.
Right.
It looks the same.
most people, when they do these things, with some exception, typically do them in a fairly standard, not terrible way. They just might not always show all their work or say all the things. Yeah.
Can you explain how you got from like multiplying
The conjugate?
and then how did like the x squared come out of the 25 and then the 19?
Totally. So first things first, let me so what I did here, so the reason we multiply by the conjugate is because it's nice. Because, okay, not more than nice. Specifically, we're trying to get rid of the radical. And so we need to multiply by something that's going to get rid of that radical and not have a middle term that's still going to have the radical in it. So the whole idea here is that we're just kind of exploiting the idea. If you multiply a minus b times a plus b, its conjugate, or vice versa, a plus b times a minus b, its conjugate, you end up getting a squared plus a times b minus a times b minus b times b. So the middle terms cancel, and you end up with a squared minus b squared. Or to say it another way, if you have a difference of squares, a squared minus b squared, it always factors as conjugates. A minus b times a plus b. Now, if we can show the work here too. So if I'm multiplying these things out, square root of 25x squared plus 19x minus 5x times the square root of 25x squared plus 19x plus 5x, we can do all the work. Now, I will tell you, as you do this more and more and more, you don't want to do all the work. You want to be using the shortcut, be like, oh, I know that I'm just going to get the first thing squared. Right? That's my a. I'm going to get a squared, and a squared is just that. Square roots minus the second thing squared. Oh, minus 5x times 5x is 25x squared. But we can also do all the work. So multiplying this by this, I get the square root of something times the square root of something is just the something. And then this times that is going to be plus 5x times the square root of 25x squared plus 19x. And then this times that is going to be minus 5x times the square root of 25x squared plus 19x. And then finally, minus 5x times positive 5x is minus 25x squared. And look, I get exactly what I thought I got. This minus this is going to be 0. And so I'm left with exactly 25x squared plus 19x minus 25x squared. And then those cancel. So that's what's happening there. As far as the other thing, sure I got room here. So the whole idea here is that when I'm dealing with this, I should be a little bit more just with my paper usage here. When we're trying to, how do I say this the right way? So here's what I'm seeing when I look at this. From this step here, I see that my highest power on top is x to the first. So cancel out the other things. So I'm trying to kind of make it look like the denominator has x to the first. And I know that the square root of x squared is x to the first, or maybe it's negative x to the first, depending on which side of infinity we're on, or which infinity we're going to. So I am kind of looking at this expression here, the square root of 25x squared plus 19x, with an eye towards, I know what I need to happen. I know I essentially need to just pull out the biggest power of x I can, which is x squared. I mean, it's going to end up being x to the first when I take the square root of it. But looking at this expression here, all I'm really thinking of, you can think of it this way. I like to think of it as just factoring out x squared and then seeing what I'm left with. But if we don't like that language, we can also say, well, really what I'm doing is I am dividing each thing by x squared. But I can't just divide by x squared. That's going to change it. So then I also have to multiply by x squared. Let me ask all of you, is this the same as that? Right. All I would have to do is distribute the x squared back through and it would cancel. But I want to leave it like this because then I'm going to say, oh, 25x squared divided by x squared is just 25. And 19x divided by x squared is just 19 over x. And then I can rewrite this as the square root of x squared times the square root of 25 plus 19 over x. And then finally, if x is positive, I can say this is just the x, not the, I don't even want the absolute value, times that. So that's what I'm doing there. I'm trying to pull out the biggest thing I can. You're welcome, yeah. Yeah. I think it's only going to work if x is the even power. Well, so let me actually point out, let's say we had something like that. So if we had maybe the limit as x goes to, let's say infinity again. I'm going to go, yeah, let's say we had something like 5x plus 1 over the square root of x cubed plus 2x plus 1. I don't know, plus something else. So here's what I would say about this. I know this limit's 0. And the way I know this limit's 0 without doing any sort of real inspection is, what is the highest power of x that's occurring in the numerator? And if you had to kind of think about simplifying things down, what's the highest power of x that's a fraction that's occurring in the denominator? 3 over 2, right? Because you have to the third, but then it's inside the square root. So it's really like, so this right, this part here, right? If I kind of ignore the lesser powers, this is essentially just the square root of x cubed, which is essentially just x to the 3/2. So what I really have here is something where the denominator is getting bigger faster than the numerator. So that's going to end up going to 0. Now, is that enough work to show? Probably not. So what would I do? Probably, yeah, you probably could. So I could totally write this as a limit as x goes to infinity, 5x plus 1 over, I'm still going to pull out the x here. So here's the work I should show. The square root of, so I really want an x to come out of my square root. So I'm gonna factor out an x squared from inside my square root. So I'm left with x cubed divided by x squared is x. 2x divided by x squared is 2 over x. And 1 divided by x squared is 1 divided by x squared. Plus x. And then that's going to be the limit as x goes to infinity of 5x plus 1 over x. I'm not going to write the absolute value. No, that's just positive. And the square root of x plus 2 over x plus 1 over x squared plus x. And then we can divide everything by x. So I've got 5 plus 1 over x over square root of x plus 2 over x plus 1 over x squared plus 1. Right, divided the top by x, 5x divided by x is 5, 1 over x is 1 over x. This thing divided by x is that, and x divided by x is 1. And then if I let x go to infinity, that's going to go to 0. That's going to go to infinity. So I end up with 5 plus 0 over infinity plus 1, which is 0. I think so. Yeah. Yeah.
Even if it's like, can you really evaluate something and say for, oh, I guess you can, never mind, ignore that.
Okay. Yeah.
Why not?
Sure. So if x is going to infinity, where's x going to? Right. So then I guess I could be a little more clear. X is going to infinity, and then 2 over x is going to 0, and 1 over x squared is going to 0. So I have infinity plus 0, which is infinity. And then I should say, what's the square root of infinity? Infinity. It kind of feels dumb sometimes when you're like, oh, infinity times 2 is still infinity, plus 1 is still infinity, minus 5, right? You can do lots of things to infinity and still get infinity back.
If the power you take out of the square root is still smaller than the power, like say that plus x was actually plus x squared,
Sure.
You divide by x squared instead.
Yeah, because we typically, so I will point out, I kind of violated my own rules here. Because technically I didn't divide by the highest power of x in the denominator. I really kind of should have divided by an x to the 3 halves. Because technically my highest power of x in the denominator is kind of x to the 3 halves. So do I have a good rationale for saying why I didn't do that? No, I don't. How do I do what?
What is that? Three times.
So another way we could have done this one, although I think we're getting a little too in the weeds here, so I'm just gonna show real quick. Another way you could have dealt with this, if you really wanted to, is to have said, and this is where things get weird, I'm gonna plot an x cubed from inside the square root, which I don't love. And then I'm left with a 1 plus 2 over x squared plus 1 over x cubed. And then if you pull that out, you have an x to the 3 halves. And then you're left with the square root of 1 plus 2 over x squared plus 1 over x cubed plus x. And then I can divide everything by x to the 3 halves. So if we do that, we get the limit as x goes to infinity of 5x over x to the 3 halves plus 1 over x to the 3 halves over this divided by x to the 3 halves plus x divided by x to the 3 halves, which simplifies to 5 over x to the 1 half plus 1 over x to the 3 halves over the square root of 1 plus 2 over x squared plus 1 over x cubed plus x over x to the 3 halves is 1 over x to the 1 half. And then this thing goes to 0, this thing goes to 0, this thing goes to 0. That should be an x to the 1 half, not an x squared. And this thing goes to 1, because it's 1 plus 0 plus 0. So you end up with 0 over 1. That's probably the more algorithmic way of doing the same thing every time. Divide by the highest power. But really what I would say is if you see something fractional like this, and you can recognize that the denominator is a quote unquote bigger thing than the numerator, it's a pretty good bet that your limit's going to be 0. Yeah.
It would not matter if x was a number.
What do you mean by if x is a number?
For the second one, there's outside plus x. If that was plus 5, and then
Right.
that would be the same exact process.
Right.
And that would just be
Right.
Basically, anything with like x and whatever at the denominator goes to 0.
As long as the power of the denominator is a higher power than the power in the numerator. I should rephrase. As long as the degree in the denominator is a higher degree than the degree in the numerator. So in this one, we totally ended up getting 0 because the highest power of the denominator was x to the 3 halves, which is bigger than the highest power in the numerator, which is x to the 1st. But we saw way back in the beginning, right? If you have, say, an expression where the highest power in the numerator and the highest power in the denominator are the same, the limit isn't 0. The limit ended up being 5 over 2. Or typically, whatever the quotient. Right, yeah, exactly. Yeah, those are going to. Right, as long as you have basically a constant over some x to some positive power. Yeah. X to the power of 3 over x to the second?
No, x to the power of 3 half. So the one we have right there, if it was going to negative infinity, it would be the same.
Nah, we can't do it. We're stuck. You can't take that limit. Why not? Indeed. Why can't you take the limit as x goes to negative infinity of x to the 3 halves power? Right, because that's really the limit as x goes to negative infinity of the square root of x cubed. That's a problem. Does not exist. Right.
Even if you do it the other way, you get does not exist.
Yep. So here's the thing to think about. You look back at your original expression for just a second here. If x is negative infinity, so in x cubed plus 2x plus 1, x cubed is the dominant term, right? It's going to overpower everything else. So if x goes to negative infinity cubed is a very, very negative number. and then adding 2x and 1 is not going to change that behavior. So this whole inside is very, very negative, and we can't take the square root of a negative number. Right, this function is totally undefined as soon as you get just a little bit slightly less than 0. I don't know exactly where, but like if x was right, if x was -1, yeah, I think even at -1, this thing happens to be negative. So this graph is really, if you graph this whole thing, the graph would only have a domain that started somewhere just slightly left of the origin. Or no, highly unlikely. What I will say though is I've definitely seen on homework assignments people ask questions like this and then ask this question as well. And I think sometimes it's a mistake and sometimes it's on purpose. I think sometimes they're thinking, oh, well, I want them to see, like down here, if it's going to negative infinity, you have to do the absolute value thing and get a negative. But unfortunately, that's not actually what happens. It totally does happen if you look back at the examples we did first. Like, for example, you look back at this example, it's totally fine to ask what happens as x goes to infinity or negative infinity, because infinity squared times 9 plus 2 is positive, and negative infinity squared times 9 plus 2 is positive. Totally safe either way here. But here it's not safe, because if x is going to negative infinity, oh wait, oh well, no, it's safe here. It is safe. It's just not very interesting, because you don't have to do all this work. If x is going to negative infinity, so negative infinity squared is positive infinity, and that's going to dominate here. So this part's going to infinity. And this part's going to minus infinity, which is plus infinity. And what's infinity plus infinity? Right. This one you don't have to do any real work for.
So infinity plus infinity is not an indeterminate?
Correct. Infinity plus infinity is fully determinate. Yeah.
So minus infinity is indeterminate?
Right. So infinity plus infinity is infinity all day long. Or twice infinity, if you like. But infinity minus infinity is, we don't know. It could be anything, literally. That's why it's called an indeterminate form. Infinity minus infinity could be infinity. Infinity minus infinity could be 0. It could be 1. It could be pi. It could be negative infinity. Anything is an option. Because the one infinity could be way, way bigger than the other infinity, or it could be way, way smaller than it, or somewhere in between. This particular example of infinity minus infinity happened to equal almost 2.
Is that what you mean? Like we're not safe there?
No, we are. So if this was, so no, so what I was trying to say, this is not a great example. What I was trying to say, yeah. What am I? I guess what I'm trying to say is, no, it's not really a good example. Yeah, or if it was like an X. So for example, if, come on, papers. I could see the potential of someone asking a question like, find, which I don't want to do right now because we've done it enough, but somebody could say like, let's find the limit of x goes to infinity of the square root of, yeah, what am I doing up here? Maybe not. Huh. Anyway, something like this, 4x plus 5 minus, I don't really, yeah, I don't know. Oh, I know what they do. They do something weird like that. That's what they do. Okay. Minus the square root of like 4x plus 1. That's an infinity minus infinity form. We'll probably do it, even though I don't want to. But then I've seen people also ask the following question. Yeah. And this one is a no. A hard no. Because if x is going to negative infinity, what's negative infinity times 4? Plus 5? Still negative infinity. And then the square root of negative infinity is no dice. Does not exist. Off the bat. Can't take square root of negative number. Doesn't work. Okay. On the other hand, this first one is a totally valid thing, and it certainly is an indeterminate form. It's infinity minus infinity. And I'm going to change up my numbers a little bit because I have a sneaky suspicion this is going to turn out to be something conveniently that I don't want it to be. So let's make this let's make this wild. Let's make this an 81. Sure. I'll probably turn a 5 to an 8. So same attack plan here. Multiply by the conjugate. The limit as x goes to infinity of square root of 4x plus 81. That's a 4, not a 9. Minus the square root of 4x plus 1 all over 1 times the conjugate 4x plus 81 plus square root of 4x plus 1. I should emphasize when you're talking about the conjugate, it's the same exact expression, just the sign connecting the two pieces changes from negative to positive or positive to negative. Everything else stays the same. Same deal down here, 4x plus 81 plus square root of 4x plus 1. And then the whole reason we multiply by the conjugate is so that when you multiply this thing times this thing, you're going to get the first thing squared. So we're going to get the square root of 4x plus 81 quantity squared minus the second thing squared, which is just the square root of, this is not going to turn out, that's going to be fine. I don't care. It's fine. 4x plus 1 squared. All over square root of 4x plus 81 plus the square root of 4x plus 1. This one's just not very exciting, but that's fine. Not everything has to be exciting. So this ends up being the limit, x goes to infinity of 4x plus 81 minus 4x plus 1. Be careful, there should be a parentheses there. Over the same spot. Now what's going to happen on top? We're left with the limit as x goes to infinity of 80 over all this stuff. And now we should be able to say what this limit is without doing really any more work. Top's a constant, and the denominator is getting larger and larger and larger. That means, yeah, we have something that's going to, something over infinity is going to go to 0. So in this particular example, it happens to turn out that the infinities were the same size. Infinity minus infinity happened to equal 0. No, at this point here, I don't think you have to show any more work. I think it's a totally legitimate expectation that you can say, oh, I have something divided by, I have something that's not changing divided by something that's getting larger and larger and larger. I think you're perfectly reasonable that that's just it. Cool. Yeah. Yeah.
It's the most I've understood this entire semester.
Well, I'm glad you're here. Tell your friends.
Yeah.
Or don't. To your friends. That's how you should tell your friends, right? Because because it is, for some reason, every year it's like, especially after we've all been kind of off campus for a while, it's hard for students to know that we are great research. By the way, if you ever are taking chemistry or physics, we also have these kinds of classes for those things as well, just so you know. Question?
So on the
Yes.
I did like use the correct way, but I know like everybody in the class got it wrong.
Okay, what was the question? Okay. I'm sure we can figure it out. Well, okay. Okay. Sure. Yep, I know what this is. Which is what you should do. Okay, which is the sandwich. Okay. 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 Right, it's a classic example, or really x to a power times sine of something or cosine of something as x goes to infinity. Here's what I want to point out. Here is the clue that you should have used the squeeze theorem or the sandwich theorem if you didn't know already. So the clue that I'm always looking for that's going to tell me about the squeeze or the sandwich theorem. Not that there aren't other times you could use it, but specifically booze with the sandwich or squeeze theorem. If you see a limit as x goes to some sort of infinity, doesn't matter if it's positive or negative, and a cosine or a sine. That is a very, very good chance of having used the squeeze theorem. So, squeeze theorem says the following. In fact, the squeeze theorem actually uses another theorem, which is, let me actually just say this first. So just so you all know, there's another theorem that's related to the squeeze theorem, and it says the following. If you have a function that is less than or equal to another function, then it's true that the limit as x approaches a of the lesser function is always going to be less than or equal to the limit as x approaches a of the larger function. Basically, you're saying if this function is always smaller than this other function, then whatever values they approach have to be smaller than whatever values they approach. Okay. Well, the idea with the squeeze theorem is kind of just abusing this a little bit. We're going to say the following. So for this sort of thing, it's always the case that we're going to start with saying that cosine, and in fact, I should point out in my list of like limits to infinity. So we kind of, this was kind of the last thing on my list, which is that you have the nice ones where it's like a nice rational function, polynomial over polynomial. Then you have kind of the less nice ones where it's maybe an infinity minus infinity that you have to make into an infinity over infinity with some square roots in it. And then sometimes you have these squeezy theorem ones. So I'm going to start off with saying cosine of whatever is in there, doesn't matter, is always between -1 and 1. In fact, here's some proof to back it up here. I don't have just the. That's not what I want. Cool. So there's good old cosine 2x, looking just like we thought it should, between 1 and -1. So it's certainly, it's going to be great. I'm going to love this. Right? Definitely underneath y equal to 1, totally above y equal to -1. And then what we're going to do is we're going to manipulate the thing that we have in the middle so that it looks like the thing we're trying to take the limit of. It's really just you get to say what you want to happen. So in this case, I want it to be x squared times cosine of 2x. So what am I going to do? I'm going to multiply by x squared to make it look like how I want it to look. But I can't just do it to the middle part. I have to do it to all the parts. So we multiply everything by x squared, or whatever you need to multiply by to get it to work. So now I'm going to have -1 times x squared less than or equal to x squared times cosine of 2x less than or equal to positive x squared. And I will show you, ooh, this was a limit to infinity. Okay, yeah, okay, yeah. Okay, so, right, okay, so this actually, so this problem is not a great, so this one written as is not going to work out. Because the problem is you have something that's getting infinitely large and something that's just kind of oscillating. So this limit is not, so even though I said these words and they are usually true, this particular thing that I wrote down is not an example of where this is going to work, which is fine. Let me show you actually though, just so you can see. We're going to fix it in just a second, but I will point out that if I then multiply everything by x squared, it is certainly true, although kind of hard to see because things are pretty wild here. That, oh yeah, my thing here is always between these two functions here. Now, I'm going to go ahead and fix this to make it a better example. I will just point out though, you wouldn't actually need to use the squeeze theorem if it was just the following. If it was the limit as x approaches 0 of x squared times cosine of 2x. Oh, good call. Thank you. If it was just the limit as x goes to 0 of x squared times 2x, although you might think you need to use the squeeze theorem, and it would totally work to use the squeeze theorem, totally unnecessary. Because before you do anything else, what should you do if you're trying to find the limit? Plug it in. If you plug in 0 for x here, I think it was a different question. I'm pretty sure I know what it is. Interesting. So I have a feeling I know why. So if I plug in 0 here, what do I get? We have to make sure that this exists though, right? If that was infinity or something weird, what's cosine of 0? Right? So you get 0 times 1, which is 0. So if this was the question she asked, or sorry, if this was the question she asked, what? Well, but I think it's a slightly different question. So just hold on. So if this was the question, then it's technically correct to just plug it in and get 0. But I don't think it was the question. Here's what I think was actually the question. I'd be willing to bet a decently large sum of money that the question was something more like the limit as x approaches 0 of x squared times cosine of 2 over x. I wouldn't be surprised if this was what that was actually asked. For a limit? Right. So again, that's what I'm gonna say. If it was the thing that I wrote before, and like if it was really x squared times cosine of 2x, it is correct to plug in 0 and get 0 as an answer. Meaning, so later on, I would love for you to show me that. Just because if that's the case, then everyone should be able to argue for this point. Okay. But regardless of whether or not that's the question, this is still something worth looking at. So what I point out here is in this example, if you try plugging in 0, ain't gonna work out. Because you get 0 squared, that's fine, but you have cosine of 2 over 0 is infinity-ish, and cosine of infinity-ish is what? We don't know. You find it? Really? Not that I don't believe it, but I just like, I believe it. Yeah. So you should not have had to do that because, so if you plug in 0, you get 0 times cosine of 1, and it doesn't matter that cosine of 1 is not a nice number, it's a real number. So your professor is wrong to mark people. Yeah. So the limit is x. So you should, I mean, I guess you shouldn't because you got it right, but you should encourage your classmates to make a fuss because your teacher is actually wrong, right? This limit is equal to plug in 0. There's no need to use the squeeze theorem here. You get 0 squared times cosine of 0 plus 1. Yeah, I don't know what cosine of 1 is. I mean, I have a good idea. It's about 1/2. But it doesn't matter that that's about 1/2. 0 times any real number, not infinity, is 0. So I'm sorry, your professor doesn't know what you're talking about. Sure. That doesn't make it good though. Just so back to this actually interesting question. Not that terrible. Not that you're terrible. Your professor asked a terrible question. Okay. So here, if we want to find this limit, we would use the squeeze theorem for real. We would say, oh, I can't deal with cosine of undefined, so I'm going to use the great piece of information that cosine is between 1 and negative. Now I'll point out that this limit still meets my criteria for having to use the squeeze theorem, which is 1, I have, well, really, the criteria is, for the squeeze theorem, in my opinion, is essentially if you have sine of something going to infinity or cosine of something going to infinity. That's when you really need it. So sometimes your limit's going to infinity and you have, sometimes your limit's going to 0 and you have like 1 over that. So Here, we're gonna say that that's between -1 and 1. Also, just want to point out, back to our graphing stuff, just kind of for fun, because it is fun. I think it's fun. Here's cosine of 2 divided by x, much wilder looking. Whoa, that's crazy. But it's still between y equals 1 and y equals -1. You can zoom out if you like, looks freaking bizarre. Okay, but now here's the idea. We're going to, just like we were trying to before, multiply everything by the thing we need so that this inequality has this in the middle. We're gonna multiply everything by x squared. So I'm gonna say, okay, great. Negative x squared is less than or equal to x squared times cosine of 2 over x less than or equal to x squared. By the way, what's your name? Ansley?
Yeah.
Can you email me that question or some sort of, I would love a reminder about that because I would love to know more about that. I want to share that with my colleagues. And I'll forget if you don't email me. So please send it my way. You can send me the whole test if you don't mind, if it's not inconvenient, but it's just that one if that. Okay, sure, just the question, totally fine. Yeah. Yeah. Well, it might be more, it's probably not just. Yeah, that's pretty typical. Right? Yeah, people, because they don't, yeah, it's unfortunately a fairly standard. Anyway. They're ruining the curve. I know those people, they're the worst. Okay, let's focus back on this. All right. I know don't get me wrong, I enjoy complaining about some professors, but I had some of the ones I had still teach here. In fact, so I was a student here many years ago, started in 1998, and one of my professors for 22A still teaches, Dr. Dedell. He's kind of great. I mean, he's definitely, I did like him. He definitely, I never had him for calculus, I had him for linear algebra, which is a different animal. He definitely was better for that. Anyway, so, I'm a math person. So we've got this inequality. And if we take the limit as x goes to 0 of the outer pieces, what happens as x goes to 0 of negative x squared? We get 0. And what happens to x squared as x goes to 0? Also 0. Right, you just plug in 0. So again, I'm going to always go back to whenever I'm trying to evaluate a limit, the very first thing we do is just try and plug it in. And if you can, great, right? Really, I should be, if I'm plugging in, I should be getting negative 0 squared. Right. Most of the time, that's going to be true. Most of the time, when you plug in their things, you're probably going to get 0 divided by 0. That's usually going to, or infinity, like you're going to get something that's crap. Yeah. And the point is, then you have to do some algebraic manipulation. But here, what's kind of cool is that we're taking our function and we are, where'd you go first? And we're multiplying by x squared, and check it out. It's totally between these other two functions all the time. And so as you get closer and closer to 0, well, since that top function x squared is getting closer and closer and closer and closer to y values that are 0, and the bottom function negative x squared is also closing in on 0, then the function that's squeezed between them has no choice but to just bounce back and forth between ever smaller and smaller and smaller numbers, getting closer and closer to 0. Super, I love it. This is a cool graph. Right? It's super neat to see that happens. So no matter how much you zoom in, right, it's just going to keep getting, right? Yeah, okay, right? It's just, so that's the real nature of the squeeze thing. If you've got some function that's probably bouncing back and forth, though it doesn't have to be, but there's these two things that are just smooshing it down to this one dot. Now, the thing about the squeeze theorem is, for the squeeze theorem to work, both of these outer things in your inequality have to have the same limit value. They both have to be 0 or whatever number they're both getting close to. But if they're even slightly different, squeeze theorem does not apply.
If cosine is the power of two itself, then it's cosine to the power of.
Cosine squared, yeah.
That will work.
It would still work. There's no need to take a square root. So let's say we're trying to take the limit, what do you want to take the limit of? The limit as. Now, that limit is not going to exist on its own. Sure. As x goes to 0. So there's a couple different ways of dealing with this. One way of dealing with this is to just do the same thing and say cosine squared of 1 over x is, well, if cosine is between -1 and 1, cosine squared is also between -1 and 1. And actually, I'm being a little too generous though. That's fine. It'd be totally fine to do this. It's totally true. It's 100% true. I'm not. Okay, but if I'm between 0 and 1, I'm still between -1 and 1. Right? If x is between 1 and 0, then certainly x is between -1 and 1. Now, I will fully say, most people would go ahead and say, but we would prefer to write the more restrictive inequality. Cool. Now I do the same thing I always do when I'm trying to use the squeeze theorem. I multiply everything by, or divide, or do whatever I need to do to make the middle part look like the thing I'm trying to take the limit of. So I'm going to multiply everything by what? Okay, so then 0 times x squared is less than or equal to x squared times cosine squared of 1 over x is less than or equal to x squared times 1. Cool. So then I have, just simplifying a tiny bit, 0 less than or equal to x squared times cosine squared of 1 over x less than or equal to x squared. Because when you square something, it's always non-negative. So you're totally right. I could totally do it this way, right? We could do this, we could do or negative x squared less than or equal to cosine squared of 1 over x less than or equal to x squared. That would also work just fine. In either case, the squeeze theorem is going to work out just fine. In this case here, the limit as x goes to 0 of x squared is 0 squared, which is 0. The limit as x goes to 0 of negative x squared is negative 0 squared, which is 0. And so since these two limits are the same, we then usually write some words like by the squeeze theorem, the limit of the middle thing is also the same value. The limit as x goes to 0 of, x squared times cosine of 1 over x, cosine squared. Works here too. What's the limit as x goes to 0 of x squared? Everybody. 0. And what's the limit as x goes to 0 of 0? Right, limit of a constant is always the constant. Oh, they're the same. Great. Squeeze theorem still applies. So the limit as x goes to 0 of x squared cosine of 1 over x, cosine squared of 1 over x has to be 0 by the squeeze theorem. Yeah.
Now, other question I have is y substitution. Now takes the place of the mod.
With y substitution.
Yeah, then we can say 1 over x is we simplify that as y and say y approaching infinity. Is that ever necessary?
I don't think so. I don't think you should do it that way.
Okay.
But anytime there's a cos or a sine, can you, like, it's gonna be in between -1 or 1?
That's always true. Cosine of anything, sine of anything, always negative 1 and 1. Now, I would point out that we don't always need to use that fact. We typically only need to use that fact if the thing that's inside is undefined in some way. So here I'm using the squeeze theorem, I'm using that inequality because the 1 over x as x goes to 0 is undefined. Yeah, it's between -1 and 1, or if it's square, which would even power, you can even make that more restrictive and say between 0 and 1.
When you wrote before, 2%, which is squeeze theorem, and then you use it when it comes to limits, if the limit of x goes to positive or negative infinity or 0.
Right. What I really should say is it's more that the clue is that, and I kind of was missing things here. The clue is more that you have a cosine of a thing or sine of a thing, and whatever x is doing, and x going to wherever it's going to, makes your thing go to infinity. It could be 5, right? For example, I could say, what's the limit? I'm gonna make it look stupid here. I could do something like, what's the limit as x goes to 5? Let me see if I can make this actually work. Cosine of 1 over x minus 5 times, I'm sure I'm gonna guess fine, 1 over x minus 5 squared. That's probably not right. No, sorry. Try this instead. Times x minus 5 squared. Oh, it's better. That also has the clue that you have cosine of a thing that's undefined, and it doesn't matter what this is. I mean, it kind of matters, but like basically that's what you're looking for. Cosine or sine of something undefined. That is not always, but pretty typically a clue that we need to use the squeeze theorem. I will probably never say something is true 100% of the time unless it actually is for sure. But seeing something like cosine of something undefined is a very, very strong indicator that you should use the squeeze theorem. Okay. So that's an excellent question. So I'm always going to fall back on, well, first, of course, I would try plugging it in, and I would get cosine of undefined, which is the problem. Time still a problem. So I would say, well, great. I know that cosine of it doesn't matter what cosine is taking of. Cosine is always between what and what. Right. And then I would actually fill in what goes in there. 1 over x minus 5. And then what do I need to multiply everything by so that the middle part looks like the thing I want to take the limit of? Exactly, right? You have very few choices when you do these problems, right? You have to start off with cosine of blah being between -1 and 1, and then multiplying it by whatever you need so that you get the thing that you're trying to take the limit of. So yeah, we multiply everything by x minus 5 squared.
There was an instance where we were pretty much doing like squeeze theorem, but like we had to squeeze like multiple different numbers. So like we had to get like the end start to be like different things.
Okay.
I don't know if I have
Sure.
that or not. Oh, I think it's
Just give me 1 second so I can wrap this
Yeah,
up and
yeah.
then So everybody should be able to tell me now, if I take the limit as x goes to 5 of this right part, what am I going to get? And what if I take the limit as x goes to 5 of this other part? Right, so by the squeeze theorem or sandwich theorem, since the limit of the right hand part as x approaches 5 is 0, and the limit of the left hand part as x approaches 5 is 0, then we get to say the limit of the middle part has to be the same value because it is stuck between these other two things that are both getting closer. That's the whole shebang. Did you find your thing?
Yeah, it has to do with like epsilon.
Oh, okay.
So I feel like it's kind of similar, but not.
Yeah, the delta epsilon proof is
So it was
it's not a squeeze theorem thing, but it's got that same flavor of trying to say the stuff between the other stuff and taking it. We're actually we were gonna talk about infinity bubbles. Yeah.
So just to clarify, you're putting the cosine thing in between -1 and 1 because the cosine graph is
Right. It doesn't matter. It doesn't matter what garbage you are taking the cosine of. It's always between -1 and 1. You can put cosine of terrible crap in here. If you can write it the right way. Try it again. Or sine, works for sine too. Cosine of, you could do 1 over x minus 5. And even though it's weird looking, it's always between y equals 1 and y equals -1. 100% of the time. Because if you think about, I guess what I'm thinking about is think about the unit circle. Right? It doesn't matter what you're taking, what angle you are taking cosine of, the highest cosine value is over here on the right side of the unit circle at +1, and the least cosine value is over here on the left side of the unit circle at -1. And that's it. You can't go further than that. You can make this stuff in here completely insanely awful. And even though it looks super, super bizarre, it's still stuck, right? We're still bounded above by 1, bounded below by -1 every single time, no matter what. And the same is true whether it's cosine or sine. It's not true for other functions, but it's totally true for sine and cosine. So hopefully you now are like, believe it in your soul. But, oh yeah, sine of anything, cosine of anything, always stuck between these two functions, these two values.
I can't see how this is always useful when x calculation is infinity. Because even one side of which may be infinity and one side of infinity all the time.
Well, so for example, someone could, this is more a more kind of typical squeeze theorem question for like infinity is something like the limit as x goes to infinity of sine of x over x. Or a more interesting variety, the limit as x goes to -infinity of 2x squared plus cosine of x over 3x squared plus 5. You can use the squeeze theorem for both of these to show that this limit happens to equal 0 and this limit happens to equal 2/3. Right, exactly. Here, you're starting with sine x between 1 and -1, and then dividing everything by x. And I think we can all see that those two limits both go where? Does it go to 0? Oh yeah, x is going to infinity, so 1 over x is going to 0. Same deal here. Similar deal here. You can say that, sorry. You can do this a couple different ways. I personally like to do it the way where you start with cosine between 1 and -1, and then you make the cosine look like the thing you're trying to take the limit of. So first you add 2x squared to everything. This is not everyone's favorite way of doing this. It's my favorite way of doing it. And then divide everything by 3x squared plus 5. And then I'm going to ask all of you, if I take the limit as x goes to infinity of 2x squared plus 1, or sorry, as x goes to -infinity of 2x squared plus 1 over 3x squared plus 5, since the degrees are the same, what's our limit going to be? 2/3. And the same is true over here. That's also going to go to 2/3 as x goes to -infinity. Not really. No, so typically, yeah, when you have a rational function and the degree on top and the degree on the bottom are the same, the limit to infinity and limit to -infinity both end up being the same value. Right. Well, so here's what I would say. If you had this expression, it's totally valid to divide everything by the highest power of x and the other thing. But here's the problem here. And so you can either do it this way, use the squeeze theorem, or you could say, I'm going to do it, take everything divided by x squared, so make the limit as x goes to -infinity of 2 plus cosine of x over x squared over 3 plus 5 over x squared. Now we know that this goes to 0 because there's kind of a rule that says constant divided by x to a positive power goes to 0 as x goes to plus -infinity. But how do we know that cosine x over x squared goes to 0? By the squeeze theorem. So if you do it this way, you typically then say, oh, we know that cosine of x over x squared is between 1 over x squared and -1 over x squared, and then this goes to 0 by the squeeze theorem. So almost all the time, when you have like a sine or a cosine, and x is going to infinity, you're gonna have to use
All the same numbers, but instead of x squared, you're both x cubed. Does that affect the -1?
Nope. As long as the degrees are the same, it doesn't matter. So the only time whether you're going to negative infinity or positive infinity really makes a difference for a rational function, meaning polynomial over polynomial, is if the degree on top is 1. Then you might get different things depending on if you're going one way or the other. Yeah, you could have a slant or even a parabolic asymptote, but yeah. Right, because if you have a slant asymptote, you're going up to infinity on one side and down to negative infinity on the other side, or vice versa. So that's kind of what's happening. In fact, there was an example of this way back in the beginning, that you might have missed. Where'd you go? I'm a little out of order here. Yeah, so if we look back just to the very beginning here, we looked at the limit as x goes to infinity of negative 2x to the fifth plus 5x cubed plus 7 over 4x squared plus x plus 1. And if you go to infinity, you do end up getting negative infinity as your answer. And I will just say, if we take the limit as x goes to negative infinity, the answer would be positive infinity. So the side does matter because one side, so as you go over to the right, you're going, in fact, why am I trying to graph it with my arms? Let's graph it for real. So here's what I would say about this before I graph it for real. Looking at the highest powers, I have an x to the fifth over x squared, which is essentially like an x cubed. So this graph is going to have a cubic asymptote, or it's going to look like x cubed, but it's going to look like a negative x cubed. So it's going to be going like this, up to the left, down to the right. So we know that as you go towards negative infinity, the limit should be positive infinity, and you go towards positive infinity, the limit should be negative infinity, like that. Well, let's actually graph it because it's good to graph things. So let's just turn that off a minute. And let's see, this is going to be a little bit less messy. So what have I got here? I said I had parentheses negative 2x to the fifth plus 5x cubed plus 7 divided by, and then we've got 4x squared plus x plus 1. Oops, don't do that, James. Cool. So there's your graph, and you can probably see even this zoomed in that as we go to the right, the graph goes down, 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 down to negative, and as you go to the left, it goes up to negative. But if we zoom out a little bit, it's a little more obvious. Oh yeah, that's our behavior. Now I will also point out that this graph really does have a cubic kind of asymptotic behavior. So if you actually graphed, it's probably this. Let me think for a second here. Do that. It's going to be I don't know. It's going to be something like this. Now you actually have to do the polynomial division if you want to see what the asymptotic behavior was exactly, but it's very similar to that function there. Just taking negative 2x to the fifth. Oh, sorry. I got my numbers backwards. Very close to that. That looks a little better. Right, you can see if we zoom in, aside from the middle where things are super janky, out to the sides, they look very, very similar to each other, which is true with asymptotes. Weird stuff happens in the middle. It's not at all what has to do with the function or the asymptote. And then as you move out towards the ends, then the function has the asymptotic behavior. Because when you're finding a horizontal asymptote or a slant asymptote or a stupid cubic asymptote, if you actually want to find this, what you're really doing is you're just taking the limit as x goes to infinity or negative infinity, which is caring about what the function is doing at the ends, but not in the middle. The middle is hot trash, and the ends are what the function actually counts. Okay, so I should also talk about the other types of things, which we have mentioned before, but it's good to say again, which are the limits. Okay, did I put all my papers down here? Yeah, I did. Sorry. Okay, come on. Also, I do post the notes from class on Canvas as well as the video from class on Canvas. Not that you really need to watch this all again, but you certainly could. But if there's something you missed in the notes that you want to see later, it'll be there eventually. Usually same day. The other thing was limits that go to infinity. Right, aka where we get very possible. So those I feel like have a much more limited range of possibilities. Sorry, I couldn't help myself. So when you have a limit as x approaches a number, not infinity, right? Infinity is not a number, it's a direction, an idea, whatever. It's not a real number. But when you have, say, like a limit as x approaches 6, let's do it one-sided first, James. of, say, x over 6 minus x. If we plug it in, so again, I'm always, at least I'm trying to always remember to just plug it in first. So if we actually plug it in, what do we get? Well, I get 6 divided by 0. Undefined. And I want to be very specific here. I mean undefined. I don't mean indeterminate. So indeterminate is a word that means it can take on any value. An indeterminate limit can be 5 or 7 or 2/3 or 19/10 or anything like 0 over 0, infinity over infinity. You can get any value. But undefined, you cannot. If something is undefined, well, technically it's undefined, right? You don't get any value. But if something's undefined specifically in a not 0 divided by 0 sort of way, we like to be more precise with how we talk about how it is undefined. So what I would really say here is, well, I have something that, well, let's pick a number. Let's plug in, like, if x is maybe like 6 point, let's make it, no, you can be smarter than that. You can make a table. Make a little table, my x's and my x over 6 minus x's. So if x was like a little bigger than 6, like 7, I'd get 7 over 6 minus 7, which is 7 over -1. If I get a little closer to 6, like 6.1, I'd have 6.1 divided by 6 minus 6.1, which is 6.1 divided by -0.1, or 6.1 divided by -1/10, which is -61. And just to do one more, if I went even closer to 6, like 6.01, I'd have 6.01 divided by 6 minus 6.01, which is 6.01 divided by -0.01, which is 6.01 divided by -1/100, which is -100 times 6.01, which is -601. It looks like things are getting pretty negative here. All right, we're going down, 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 down. The closer and closer we get to 6 from this side of 6, the more and more negative this function gets. So what we would say is, even though this limit doesn't exist, because the function, so I want to say very clearly, the limit doesn't exist because the function is not getting close to one particular number. And for a limit to exist, the function has to be getting closer and closer and closer to a specific value. Infinity is not. Infinity is not a value. It's not a number. Well, we are going to, but we're going to talk about why. So it's totally true that we're going to say that this limit, as x approaches 6 from the right, here's what I would actually do if I was doing the work. The work I like to show for this is I like to plug in 6, but a slightly positive 6. So on top, I'm just going to get 6. On the bottom, 6 minus a number that is a tiny bit bigger than 6 is a tiny bit positive or negative? Tiny bit negative, right? 6 minus a little bit, oh yeah, right, a little bit negative, yeah. So I have 6 over, here's how I like to write it. I have 6 over a slightly negative number. The left side of 0, if you will. Now I have a fraction. And the top is positive and the bottom is negative. And a positive number divided by a negative number is a number. And we know it's going to be negative infinity. Because whenever you have division by 0, I should say not 0 division by 0, it's always going to get infinitely large. Or in this case, negatively infinitely large. So what I would say is the limit as x approaches 6 from the right of x over 6 minus x does not exist, but it does not exist specifically in a way that is getting more and more and more negative. So we write that the limit is equal to negative infinity to indicate that we know what has happened. I don't think you even have to use the table personally. So let me just show you the other side so let me show you really how much work I would actually do if I was asked to do this question. If I was asked to find the limit as x approaches 6 from the left-hand side of x over 6 minus x, I would be thinking off onto the side. I'm thinking like 5.9. I'm not actually going to plug in 5.9, but that's what I'm thinking. So then I'm going to plug in 6. But I'm going to recognize that in the denominator, I'm actually picking a number a tiny bit smaller than 6. So 6 minus a number that's a little bit smaller than it is going to be a little bit positive. So now I have a positive divided by a positive, which is positive. Positive what? So, and this is all the work I think you need to show, unless your professor says you need to do more than that. So here's what I would say about limits of this type. Meaning, if you have a limit, the limits of the not 0 over 0 type. Three things can happen. Thing one, the limit could be infinity. Thing two, the limit could be negative infinity. Thing three, if it's a two-sided limit, the limit could not exist. So in this previous example, we had the limit as x approaches 6 from the right of x over 6 minus x is equal to negative infinity. We had the limit as x approaches 6 from the left of x over 6 minus x is equal to positive infinity. And then, since these two limits happen to go towards different directions, it would mean asymptotically, we have a vertical asymptote that's doing different things on either side of 6. From the right side of 6, we're going down to minus infinity. From the left side of 6, we're going up to positive. I don't know what the rest of the graph looks like. I'm just saying I know around the asymptote, that's what's happening. And then if we were asked about the two-sided limit, we would say, oh, well, since the left side and the right side are doing different things, the two-sided limit would be not existing. So when you have a non-zero over 0 type, only one of three things can happen. You either get infinity, negative infinity, or if it's two-sided, you could get it not existing. But you could also get it existing. And I'll show you that in a second. I will also say one-sided limits are always going to either be a real number or some sort of infinity or negative. Well, that's not okay. I think of that. One-sided limits of this type will always be some sort of infinity or negative. They will never not exist. There are other limits that don't exist at all. Just to point out, right? This limit does not exist at all from either side. It just keeps oscillating back and forth. Right, we've seen the graph of it like a couple times. This is that, right? It never gets close to one particular value. So sometimes the two-sided limit doesn't exist because the left side and the right side, one's going down, one's going up. But sometimes it does. I'm going to reorder these things here. So, yeah, okay. So I try to keep my papers in order, but they often get out of order. We could have something that was like maybe the limit as x approaches. Sure. Limit as x approaches 5 of x cubed minus 1,000 over x minus 5 quantity to the fourth. Yeah, I like that. And so we're asked about this, and to typically deal with a limit like this, well, first I would just try plugging it in, right? Always, even though sometimes I forget, plug it in. If I plug it in, I'm going to get 5 cubed minus 1,000 over 0 to the fourth, which is 125 minus 1,000. Well, I mean, divided by 0 is kind of the stopper there. I should probably not keep going. That's a problem. But that's a problem I know how to deal with, because now I know that I have a not 0 number over 0, which means I'm either going to get infinity, negative infinity, or not existing. Now, to determine what it is, since this is a two-sided limit, I'm going to have to look at each of the one-sided limits and see if they're both going in the same way or not knock around my finger. Okay. So let's look at the limit as x approaches 5 from the right. So if I plug in 5 from the right, my numerator is 125 minus 1,000. And my denominator is a number that is slightly positive and then raised to the fourth power. So I end up with a negative 875 over a very slightly positive number which is overall, which sort of infinity? Really, you're just looking for the sign, right? Once you see that it's a non-zero divided by zero, your only real job left to determine is the thing positive or negative, which just means you have to look at it. The numerator is positive or negative, the denominator is positive or negative, and then see how they divide. But you always want to simplify down to just see what the signs of the top and the bottom are. And then we do the same thing from the left. Limit x approaches 5 from the left. I'm still of x cubed minus 1,000 over x minus 5 to the fourth. Plugging in 5, still the top is still negative 875, right? It didn't change. So there's jamming an actual 5 in there, not something close to 5. And the bottom, I'm thinking a little more carefully, oh, a number smaller than 5 minus 5 is slightly negative. But then I'm raising it to an even power. And a negative number to an even power is positive. A positive number to an even power is positive. So I still have a negative 875 over a very, very slightly positive number, which is still going to result in a negative infinity. So since the left side and the both side are both going down to negative infinity like that, the overall limit is also negative infinity. Right, that's what you have to do. Typically, some algebraic manipulation, or if it's sine x over x, like a trig thing. I will again reiterate just to be super extra clear about it. Technically, this limit does not exist because it's not getting close to a specific number. But what we are doing is we're saying, so really when you write this, what you're saying is, I know the limit does not exist, and I know it specifically gets very, very, very negative. That's what you're saying when you write this. I would not worry too much about that. I just want to be clear. Let's see. What else can we talk about in these last 9 minutes here? You go. By the way, in general, if you need to leave early, use the bathroom, whatever, you're always welcome to come in and out. Totally fine. I understand people have other classes across campus, so feel free to go. All right. We got 8 minutes left. What else should we say? We can do more examples like that. Or do you want to do some 0 over 0 limits? Okay, let's do some 0 over 0. So I will let me say the list of 0 over 0 things. So for limits of the 0 over 0 type, limits of the 0 divided by 0 type, there are 3 algebra things and there's a couple other things. So first of all, before you even try to do anything, you should have plugged it in to make sure it was a 0 over 0 in the first place. So some things we can do are algebra. Do algebra. For example, if your limit was x approaches 5 of x squared, gotta make sure the math works. Give me a second. Oh, brain, come on. Minus 6x plus 5 over x squared minus 25. That's a 0 over 0. Let's plug it in. You plug it in, you get 5 squared. It's 25 minus 30 plus 5. 0 over 0. That would be a factor and cancel sort of situation. That would factor as x minus 5 times x minus 1 over x minus 5 times x plus 5. And then the problem factor should cancel out. By the way, if you're thinking it's a factor and cancel sort of situation and plugging in 5 is what your problem is, then x minus 5 should be a factor because that's what's giving you 0. So those cancel, boom, boom. And then the remaining part is nice. You can totally plug in 5 there and get 4 over 10, which is 2/5. So just as a reminder, this indeterminate form can take on any value. In this case, 2/5. So 0 divided by 0 ends up being 0.4. Sometimes it's 17, sometimes it's 9. It doesn't, right? It can be anything. You also have the possibility of maybe having to multiply by a conjugate. So for example, if I want to find the limit as x approaches 7 of 3 minus the square root of x plus 2 over, do I want to make it terrible? Not really. I'm going to do it anyway. 49 minus x squared. There is some factoring and canceling to do, but there's also a conjugate I have to deal with. So here you would multiply by the conjugate. I will point out in all of these algebraic things, after you do a thing, there is typically a factoring and cancel that happens after. So whether you're multiplying by a conjugate or using a common denominator or just factoring and canceling, typically after you do the first step, there's usually some additional factoring and canceling to do. Because you're always trying to make the problem factor cancel. So let me just ask everybody. Plugging in 7 is giving me 0 over 0. So eventually, what kind of factor would I like to see show up so it can cancel out? Exactly, x minus 7. Or maybe we're going to get slightly unlucky, it's going to be 7 minus x. But we're looking for x minus the thing that's a problem, or really the thing that you're approaching, or the thing that you're approaching minus x to factor and cancel. Here, the work is a little bit less nice. We're going to multiply with the conjugate, so we're going to have the limit as x approaches 7 of 3 minus the square root of x plus 2 over, I'm going to factor the bottom since I know I'm going to need to. I'm going to have a 7 minus x times a 7 plus x. I do want to be explicit here. This does not factor as x minus 7 times x plus 7. It is 7 minus x times 7 plus x. It's always whatever the first thing being squared is minus whatever the second thing being squared is, and the order does matter. Specifically for 7 minus x versus x. And then we're multiplying by the conjugate, which is 3 plus the square root of x plus 2 over the same thing. Whenever you multiply fractions by conjugates, you always actually multiply out the conjugates and you do not touch the things that are not conjugates. So we're going to multiply at the top and get 9 minus x plus 2. This is going to work out very nice. On the bottom, we're just going to leave it as all that junk. 7 minus x times 7 plus x times the 3 plus the square root of x plus 2. We can simplify, and 9, this is why the parentheses are important, by the way. This is 9 minus x minus 2, which becomes 7 minus x. So all this on top here is just 7 minus x, and we got lucky, that's already there. So that's totally going to cancel with 7 minus x right there. So that's going to equal the limit, as x equals 7, of 1, right? Because when things cancel, we're divide out, we're left with a 1 over 7 plus x times 3 plus the square root of x plus 2. And then when you plug in your 7, you end up getting 1 over 7 plus 7 times 3 plus 3, which is 1 over 84. So you can either factor and cancel, you can multiply by a conjugate, or the third kind of algebraic method for dealing with a 0 over 0 type of limit is something I don't have enough room for here, maybe, is if you have something like the limit as x approaches 3 of, sure, sorry, brain, 2 over x minus 2/3 over x minus 3. We're going to multiply by the common denominator. This is a common denominator situation. So I would multiply 2 over x by 3 over 3. I multiply by 2 over 3 by x over x. And I would rewrite this as, I should say, before I did any of that, I checked to make sure that when I plugged in 3, I got 0 over 0, which I did. Right, 2/3 minus 2/3 is 0, minus 3 is 0. And then we're going to say this is the limit as x approaches 3 of, let's see, 6 minus 2x over 3x. And instead of having fractions and fractions, instead of saying I have 6 minus 2x over 3x all over x minus 3, this is dividing by x minus 3, let's multiply by 1 over x minus 3. And then I've run out of room. This becomes, sorry, I'll try to squeeze it in here. On top, I can factor out a -2. So if I do that, I've got the limit as x approaches 3 of -2 times -3 plus x, or x minus 3 over 3x times, let's put the x minus 3 down there. And then the x minus 3's cancel. Boom, you plug in 3 for x that remains, and you get -2/9. So those are the three main algebraic methods of dealing with a 0/0 type of limit. You either factor and cancel, if it's just like nice polynomials, or you multiply by a conjugate if there's a square root, and then factor and cancel. Or if there's fractions in fractions, you get a common denominator and then factor and cancel. You're always trying, like, so in each of these, right? X is approaching 5, I was trying to factor and cancel an x minus 5. X was approaching 7, I wanted to cancel an x minus 7, or in this case, a 7 minus x. Here, x was approaching 3, I wanted to cancel an x minus 3. You're always looking to cancel x minus whatever x is approaching. All right, it is 11:50. I should stop talking and let you go. You're all very welcome, as usual. Today's Thursday, right? Make sure you fill out the attendance form if you didn't already, and I'll get these notes posted up, and I'll see you all next Tuesday.